Hello children, this is the second part of our lesson number 8 video, heat and temperature. In this video, we will be learning about the gas part, which is you will be having an idea about the internal energy and how internal energy concept goes with potential and kinetic energy on molecules, and we will be using about factors that we can get on ideal gas behavior, and when we add on those factors we will be having ideal gas equations. We will search about them, and we will have another relationship between kinetic energy and temperature in Kelvin. There is a relationship between them. So all these things we will try to learn through this video. Okay, as I told you, we will start by learning about internal energy of a substance. Now what you have to know is, when a substance is there to be seen, you don't see the inside of a substance, but inside of a substance molecules are there. They have vibrations or random movements. So they have a kinetic energy, and also they have some potential energy between them, right? So the addition of potential energy and kinetic energy of molecules inside a substance is known as its internal energy, right? And I will tell you another fact here to remember. Potential energy is always about the bondings. This is just to remember, okay? That means when a substance changes its state, for an example, water, liquid water becomes vaporized and become gas, there the only change happens is in potential energy. Potential energy increases. Nothing would happen to kinetic energy, right? And remember, kinetic energy is the energy that relates to the temperature. So during a state of change, as nothing happens to the kinetic energy, nothing would happen to the temperature. So temperature would remain constant. That means liquid water at 100 Celsius will convert into vapor at 100 Celsius. Temperature didn't change. Okay. So as I told you, potential energy accounts for the interatomic bonds between particles, and average kinetic energy accounts for the motion or vibration of particles. So I told you that potential energy changes during a change of state, and the temperature change occurs due to the change in kinetic energy. So we'll remember them nicely. You have two examples. I told you about the first example. Now we'll see about the second one. When the temperature of water rises from 20 Celsius to 80 Celsius, that means only kinetic energy of water molecules would increase. Potential energy would remain constant because there is no state of change. Okay, so as I told you that there is a relationship between kinetic energy and temperature, what is that equation? The equation is half mc squared is equal to 3/2 kT, where k is the Boltzmann constant. It is a constant, you will receive it in your paper, don't worry about that. T is the absolute temperature, and c square is the mean square speed. That is a bit of a new thing for you. However, mean square speed will directly be given to you in your papers in most of the times. Suppose they have not given, we'll try to learn how to find the mean square speed. Very easy. You square the speed of each and every particle and add them. Square the speed of each and every particle and add them. And divide it by the number of particles. So you would get what? Mean, because you divide it by the number of particles, square, because you squared all the speed. So it's not very hard. We just calculated what? Mean square speed. Now you know the idea behind mean square speed also. Right. Hereafter we will see some laws. At the end of this we will try to learn how they are being used in our questions. Right. Always remember, when we talk about these gas laws, we can only apply them to ideal gas. Right? We can only apply the gas laws to ideal gas. So in all our calculations related to gas law equations, one major assumption we make is what? The gas behaves as an ideal gas. Right, our first equation, P1 V1 equal P2 V2, it is known as Boyle's law. It comes from the fact that pressure of a gas is inversely proportional to its volume. Okay, but there are some constraints we have to limit. We have to make sure that mass of the gas and temperature of the gas remains constant. Now how would you know it? Now you can see that here there is a little bit of a gas trapped. We can pump. When we pump it, we can measure the pressure that we exert on this gas. And we can measure the volume of this gas also. Cross-sectional area multiplied by length. And finally, when we plot a graph of pressure against 1 over length, or even it doesn't matter when we write 1 over volume, because cross-sectional area is constant, so volume is proportional to length. So you can write anything here. But according to that one, these coordinates would change, but shape of the graph will be the same. So we saw that pressure against 1 over length or 1 over volume graph is a straight line passing through the origin, stating that pressure is inversely proportional to volume. Boyle's law. From that it gives us this equation, P1 V1 equals P2 V2. Right. Charles law. That is also, we can use it for an ideal gas only. There we say mass of the gas and pressure of the gas remains constant. In such cases, volume is directly proportional to absolute temperature. Don't forget this one. They may give you Celsius, use Kelvin only. Right? This is not like earlier I said change in temperature in Celsius equal change in temperature in Kelvin. That is for equal MC delta theta, first part of this video. But here in gas laws we are directly using the temperature, so always convert it into Kelvin and use. What would you do if you have a doubt whether you have to use Celsius or Kelvin? Always use Kelvin. Then no worries. Why? Standard unit of temperature is Kelvin. Right, okay, we learned that now volume is directly proportional to absolute temperature. It suggests that initial volume divided by initial temperature would always be equal to at another time volume divided by at that moment temperature. Then pressure law. Pressure law says for an ideal gas, definitely, when mass of the gas and volume of the gas remains constant, Pressure is directly proportional to temperature in Kelvin. Direct proportionality. How would you find it? We will heat up some amount of air. Then we will measure what happens to the pressure while measuring the temperature also. So we can see that when temperature, absolute temperature increases, pressure also increases linearly. It is a graph passing through the origin. So definitely what can we say? Pressure is directly proportional to absolute temperature. So we have an equation P1 over T1 equals P2 over T2. We were talking about ideal gas all the way long, but we never talked what it is. In an ideal gas, these are the assumptions we make, or these are the properties that we need to have. They are, we say that molecules have a negligible size, molecules are identical, and collisions are perfectly elastic. That means no kinetic energy is lost during collisions, and the collision time is significantly smaller than the time between collisions. This says that there's negligible potential energy. Then molecules exert no force on each other except during collisions. Because of this statement, time of collision is significantly smaller, then only we can say molecules exert no force on each other, because they are not being closer to each other for a long time. So no electrostatic repulsive forces would occur. There are enough molecules so that statistics can be applied. That is, we know, we calculate the mean square speed, average mean square speed, average kinetic energy. All those things can be done when we have enough number of molecules, and we have know that motion of the molecules is random. After we use an ideal gas, we have equation of state for an ideal gas. This is PV equals capital N capital KT, where capital N gives us the number of molecules in the gas, K is the Boltzmann constant, T is the absolute temperature, pressure and volume. Pressure of the gas, volume of the gas, number of molecules in the gas. This is a constant, and this is the absolute temperature in the gas. Now we will see an example. So it talks about a beach volleyball has a fixed volume, and the volleyball is filled with air at a pressure of 1.24 into 10 to the power 5 Pascal. And they have given us the temperature also. And they say that there is a temperature drop. There is a change in temperature. And one assumption also told, volume remains constant. Temperature is changing, volume is constant, that means pressure will be definitely changed. So they are asking, show that the pressure exerted by the air inside the volleyball is now this. How would you find it? We know the equation, isn't it? P1 over T1 equal P2 over T2. We'll rearrange it. So it gives us that P2 is equal to T2 over T1 times P1. So T2 273. Now you can see that temperatures are being converted to Kelvin. Don't forget to do that. And multiplied by the pressure, initial pressure. So we get what? The final pressure in Pascal. As it is a show that. And the show that is for two significant figures. Keep your answer for more than two significant figures. Okay. Now the second part of this example, it says that temperature of the air inside the volleyball remains constant, and they ask us to calculate the number of air molecules. Then what equation comes to your mind? PV equal NKT. So we'll subject n, it will be equal to PV over KT. 1.24 into 10 to the power 5 Pascal into volume 0.0051 meter cube divided by K. It's a constant 1.38 into 10 to the power minus 23, which will be given for you in the formula sheet, multiplied by temperature 0, 273 Kelvin. That minus the new pressure 1.14 in 10 to the power 5 into same volume 0.0051 meter cube divided by KT, because temperature also remains constant. So we get the number of molecules 1.35 into 10 to the power 22. That means we know that volleyball reduced its pressure because the temperature reduced. Now we have to increase the pressure back to its normal value by putting more molecules. We did a calculation now to find how much of molecules required to be placed in, and we identified that we have to put 1.35 into 10 to the power 22 air molecules should be placed in. Right, we'll see another small example. Now you saw from the previous example that whatever we learned in gas laws can be checked. Okay. So it talks about a light bulb, and it says that the bulb may be filled with a mixture of gases to reduce vaporization of the filament. The gas bulb contains a mixture of krypton and xenon. Right? However, the mean square speed of the krypton molecules is given. Calculate the mean square speed of xenon molecules. Mass of one molecule of krypton is given, mass of one molecule of xenon is given. So when we talk about mean square speed, it always comes from the kinetic energy equation, and you know that K is a constant. So in this equation we made sure that the temperature is also the same. That means m and c squared are the only two variables. Then we will try to find a link. Now we forget about all these constants now. M is equal to a constant divided by c square. It means m is inversely proportional to c square. So that gives us an idea that the ratio of the masses between krypton and xenon would be equal to the inverse of ratio of mean square speeds. So now we will subject mean square speed of xenon and substitute all other values and get down the answer for mean square speed of xenon. Initially we thought that it would be a very hard question, but when we understand the fact of inverse proportionality, it becomes very easy. Okay, we learned in this video about internal energy, that is the total of kinetic energy and potential energy, and we learned about gas laws, Boyle's law, Charles' law, pressure law, universal gas law, and we also learned about ideal gases and mean square speed. I hope you all understood everything. Okay children, then thank you.